So we have said, polar molecules behave different from nonpolar molecules. And one way that they behave differently is things like this. What holds the molecules of a liquid together? What causes the liquids to stay near each other in a vessel like this instead of escaping out of the beaker all the time? It's called intermolecular forces. And intermolecular forces are often the result of a polar molecule interacting with itself, interacting among itself with other polar molecules. So we've seen water before, and we've said water is a polar molecule. Water has a partial negative on each of the oxygens in water and a partial positive on each of the hydrogens in water. That's because these electrons, although they are shared, they are unequally shared because oxygen is more electronegative than hydrogen. So that unequal sharing causes a dipole to point toward the oxygen, away from the hydrogen, giving hydrogen partial positive, oxygen partial negative. Whew. That's true of every water molecule that ever existed. Partial negative on the oxygen, partial positive on the hydrogen. So because of this, you can get water molecules to align and have some interaction with each other. So this partial positive of this water molecule can interact with this partial negative of that water molecule. That little blue dot, dot, dot bond is showing that interaction. This partial positive of this water can interact with that partial negative of that water. This partial negative can interact with that partial positive. We could draw some more partial sharings over here. I'll draw one more, sure, just because. Every water molecule is going to interact like this. So the black solid bonds are regular covalent, polar covalent bonds. You might think of them as intramolecular forces within a molecule. The blue bonds are intermolecular, intermolecular, between two different molecules. Intermolecular forces are what need to be broken for a chemical to boil. So when you break enough intermolecular forces, you send these little gray dots out into the atmosphere as gaseous molecules. These little blue dots are still an intact H2O, but it's just been separated from all these other little spheres it's interacting with. Intermolecular forces are what need to be broken for water to boil. Intermolecular forces are what need to be broken for ice to melt and become liquid. We are never breaking intramolecular bonds when we melt things and boil things. Never, ever. Okay. The bond itself requires 400 kilojoules per mole to break. The intermolecular force, 40 kilojoules per mole to break. Much easier to break intermolecular forces than breaking down the molecule into different atoms. So how do we see these intermolecular forces? How do we measure these intermolecular forces? Well, we measure things like boiling point and melting point. Those are two obvious things. Delta H of vaporization, that means the energy required to take something from the liquid state to the vapor state. Vapor pressure, that means how many molecules are existing in the air, how many molecules are in the vapor around a substance. It's a terrible definition. Viscosity, that's like how thick something is, how syrup-like something is. Maple syrup has a very high viscosity. It's a very thick resistance. Viscosity is actually resistance to flow. Maple syrup is very resistant to flow. When something has strong intermolecular forces, strong attractive forces, it's going to have high values for these properties, except one. There is one outlier. Vapor pressure, if something has high boiling point, you can say it has strong attractive forces. High melting point, it has strong attractive forces. High viscosity, strong attractive forces. High delta H vaporization, strong attractive forces. High vapor pressure, weak attractive forces. So for all of these, when you have high values, it tells you you have strong attractive forces. But for that last one, it's the opposite. Okay. So there are various types of intermolecular forces, and we will name these types. Forces that involve the electrostatic attraction, just the attraction, between different molecules. They range between 40 and 0.1 kilojoules per mole. So we showed you the water one was 40. Water is among the strongest of the intermolecular attractive forces. There are lots others that are weaker. A name of the first one is a dipole-dipole force. Dipole-dipoles only exist between polar molecules. So you see how all this stuff is building on each other? You got to be able to draw Lewis structure. You got to be able to know its shape. You got to know if it has bond dipoles and if those bond dipoles cancel or not based on its shape. If they don't cancel, it's polar. If it's polar, it has dipole-dipole forces. Yep. Anything we would consider polar has dipole-dipole forces. HCCl3, that's chloroform. Chloroform definitely has dipole-dipole forces. It's a tetrahedral molecule. Those three chlorines are definitely pulling the electron density toward them, meaning it's a polar molecule. The negative side of one molecule is attracted to the positive side of the next molecule. The negative side of one molecule is attracted to the positive side of the negative one, positive, yep, There are a few examples of some dipole-dipole forces, something between polar molecules. Ion dipoles, so this is in a pure solution of HCCl3. In a pure solution of this, there is dipole-dipole interaction. For an ion dipole to exist, it has to be between an ion and a polar molecule. So this top solution is going to be between mixtures of things. This top one does not exist in a pure substance. You have to have an ion and a polar molecule together. So like when sodium chloride dissolves in water, the sodium side, the sodium cation, is always attracted to the negative end of your water in your solution. The chloride anion is always attracted to the H end of your water because the H is partially positive. Dipole-dipole versus ion dipole is stronger. That's because dipole-dipole is a partial charge attracted to another partial charge, and ion dipole is a full charge attracted to a partial charge. So when you have a full charge, that makes the attraction stronger. Okay? Ion dipole, dipole-dipole. Then there's dispersion. Dispersion forces are also known as London forces, also known as van der Waals dispersion forces. Attractive forces between nonpolar molecules from an induced dipole. Yep, we're going to say more about that. Let me just give you that definition for a second. All molecules, literally every single molecule, can interact through dispersion forces. Not every molecule can do dipole-dipole. Not every molecule can do ion dipole. But every molecule can do dispersion. So we've got a lot more to say about dispersion. Two nonpolar molecules are attracted by dispersion forces. So if I have these two hydrocarbons, we've said before hydrocarbons are considered nonpolar. If we went through and added up all the dipoles, these hydrocarbons really are nonpolar. So you would think that these two are not really attracted to each other. And for the most part, they're not very attracted to each other. But when these two molecules come close to each other, a temporary, instantaneous dipole happens, where there's a buildup of negative charge on one side, one face of the molecule, which creates a positive buildup on the other side, the other face of the molecule. My laser's not showing up at all today. So we got a partial negative, partial positive buildup, temporarily, instantaneously, and because these molecules are close to each other, this one molecule that started the partial positive negative buildup forces its neighbor to behave the same. It forces the neighbor to have a partial positive, partial negative alignment like that, which instantaneously attracts these two things together. It's an instantaneous dipole. Typically, dispersion forces are the weakest. So we've got dispersion as the weakest, and then we've got dipole-dipole next, and then ion dipole, because that's a full positive attracted to a partial, and then we got another kind. So dispersion forces are stronger and weaker based on how well those molecules can align. So if you have a large surface area, you can have a lot of intermolecular forces when that instantaneous dipole forms. I'm doing all kinds of hand motions over here. That instantaneous dipole forms along the whole length of this molecule. Well, when the instantaneous dipole here forms, even if it forms along the whole length, you've got this branch sticking out that does not allow these two molecules to get as close together. So when these two molecules can't get as close together, there's not as much attractive force between them. So this one has more dispersion interactions than that one does because of the surface area. It's still dispersion, it's still weak interactions, but the bigger molecule, the more spread out molecule, has more dispersion forces than this one. So we can see that in the boiling point. This one is 125, this one is something lower. This one is delta H of 41.5, this one is something lower. This one has a vapor pressure of 11 torr. This one is something higher because vapor pressure, remember, the higher vapor pressure means weaker forces. So we need to be able to compare two molecules that both have dispersion and tell which one has stronger and weaker dispersion. Whew. The strength of your dispersion forces is all based on something called polarizability. Polarizability tells you how easily the electron cloud around your atom can be distorted. I use the word squishy. Something that is very polarizable has a very big and squishy electron cloud. Something that is not very polarizable has a very small, hard, compact electron cloud. Polarizability increases with number of electrons. Higher electrons gives you a bigger, squishier, polarizable, more polarizable electron cloud. The more diffuse, the more spread out your electron cloud is, the greater polarizability it has. So all of these things have the same number of valence electrons, but you get to bigger and bigger atoms. Ci4 is a much bigger molecule than CF4, so that electron cloud gets more diffuse and bigger as you're having these bigger radius atoms. So more polarizable, stronger dispersion forces. Yeah, that's all I want to say. Dispersion forces usually increase with molar mass as well. Period. The end. Okay, so we've got dispersion, ion dipole, and dipole-dipole. But there is a special type of dipole-dipole interaction called a hydrogen bond. Hydrogen bonding is our last type of intermolecular force that we will talk about. If I map these elements on the periodic table according to boiling point, higher molar mass, higher boiling point. So these are decreasing molar masses, decreasing boiling points. Yep. If that's for my carbon group 4A. Group 5A, higher molar mass, higher melting point until, ooh, that's weird. My next period, oh, what the heck is happening to all my little circles? If I go through my next group, higher molar mass, oh look, that's weird. Oh look, that's weird. There are these three anomalies that do not follow the pattern of higher molar mass, higher boiling point. These three molecules are small molecules that have unusually high boiling points. That's because they have this special interaction known as a hydrogen bond. What is a hydrogen bond? A hydrogen bond is an extremely strong dipole-dipole. So it's still a type of dipole-dipole, but it's more specifically referred to as a hydrogen bond. A hydrogen bond is a dipole-dipole when you have a hydrogen directly attached to a very electronegative nitrogen, oxygen, or fluorine. Hydrogen bond, we don't talk about, hold on, let me draw. We're not referring to this thing as a hydrogen bond. No. we're referring to the interaction between this kind of molecule, this purple dotted bond, although it's not dotted because I dotted it too much. This is a hydrogen bond. So students confuse this all the time. A hydrogen bond is a type of intermolecular force. But the way you know that a molecule should have hydrogen bonding is when you have this type of bond, a hydrogen directly connected to nitrogen, oxygen, fluorine. So in order to have the intermolecular force of hydrogen bonding, you must have the intramolecular force of hydrogen directly connected to nitrogen, oxygen, fluorine. Yeah. Because the electronegativity of those are so great, the dipole is large. This is a type of hydrogen bonding. This is a type of hydrogen bonding. This is a type of hydrogen bonding. It's the intermolecular force in all of these. It is not these covalent bonds. Hydrogen bonding is not a type of covalent bonding. Have I preached that enough? Did you get it? I hope so. The reason that the base pairs in our DNA pair the way they do is because of hydrogen bonding. Adenine and thymine are the ones that always pair because there are 2 hydrogen bonding sites between those. Cytosine and guanine are always the ones that pair because there are 3 hydrogen bonding sites between those. The base pairs pair the way they do because of hydrogen bonding. Hydrogen bonding is a big deal. Okay, I'm done. I think. Yeah, I'm done.